Give it a few seconds.
So it captures that image. So you go
and then I go to
main with sponsors, recording.
Then I go to main, use me the most. And I maybe turn it a little bit and get him in the frame.
Gotcha.
And he's going.
So then hit stop recording when he's finished?
Yep.
I can do that.
And it's getting all ambient sound, just to let you know, so don't say anything too private.
Right.
What's that? Hello, everybody. I'm Jeremy Curran. I'm a pen tester here in Louisville for a local transportation company. And spend most of my time doing pen testing at work, or also doing some teaching. I teach web application security and also computer security for some universities around here. So today I was going to go over path relative style sheet injection. And to start with, I'm going to do a very quick review on cross-site scripting, just to kind of lay the foundation. So cross-site scripting is a computer security vulnerability. It affects web applications. And it's a way of violating the same origin policy protection that is built into web browsers. It's a fairly powerful attack against clients that are using the browser. It can interact with the web page, change the web page, and can even interact with the browser and take partial control of the browser itself. So it's pretty common attack as well. It's been around for 10 or 15 years, pretty heavily, and really hasn't gotten a whole lot better over the last decade. Some improvements have been made because the frameworks that you program with, like ASP.NET, Java, and such, have got some built-in protections and some functions that help the developer output and code and do some other protections, but still a fairly popular exploit even today. So generally speaking, scripts that developers include inside their web pages are allowed to run on the web page. That makes sense. You can run style sheets inside your web page, and JavaScripts, VB scripts, and other types of script to enhance the user experience, to change the page dynamically as the user is interacting with the page, and do all sorts of other tricks with the page. There is a bit of a loophole in this, in that if the attacker can somehow trick the web application itself on the server into including a script that the attacker chooses, they can fool the browser into thinking that the attacker script came from the web server, because it did in this case, and the web browser will go ahead and execute this malicious script in addition to executing all the scripts that the developer intended to include on the page. The path relative style sheet injection takes advantage of this loophole and is a type of a cross-site scripting attack. So the same origin policy generally would not allow this to happen. If you look at the example on the screen, we have google.com, and it has a home page in this mythical example. So the same origin policy is looking at the protocol being used, in this case HTTP. Of course, it could also be HTTPS. The domain, www.google.com, and then the port. Now, you don't actually see the port in the URL, but it's implied to be 80 because the protocol is HTTP. The browsers will automatically use port 80 if HTTP is the protocol, unless you explicitly list the port in the URL. You can do that with a colon, and sometimes you'll see websites using port 8080 or something like that, and you have to have that included in the URL in those cases. If you're using HTTPS, then the port is assumed to be 443 unless otherwise specified. So in the script on the bottom here, if that script were included in the google.com homepage, that script would execute, but it wouldn't be able to interact with the page. It would not be able to interact with the browser very much. That script from Yahoo would be severely restricted in its ability to change the page or even read the information on the page at all. It also couldn't do things like read the cookies or other, there's other limitations that the browser places on that script. So in this list here, there's only one of these URLs that the Yahoo script.js would be able to work with. And that's the fifth one down, because the one that's bolded, because we have the same protocol and the same domain and the same port for both the script itself, where it's coming from, and the page that's served. Everything matches. The way the reflected cross-site scripting works is that the attacker will try to send a script to the server, hoping that the server will take that script, incorporate it into the web page, and then send the web page back to the user. When this happens, the script is being included in the actual web page itself. It's not coming from a different domain. So to use our Google example, the script in this case wouldn't be coming from Yahoo and being executed in a Google page. It would be as if you tricked the Google page into including the script into the actual Google page, and when the page came back, it would already be in there. So there would be no same origin policy violation because they would literally be coming from the same place, the same origin. The browser would see this script as being deliberately included by the developer, and it would go ahead and execute the script. So we have a script here at the bottom. This is an example of a possible attack. So in this mythical domain vulnerability, it takes in a parameter, the last name. It's got an LNAME parameter here. And we can see that a script is being passed into the argument. Now, of course, the developer probably intends for last name to be an actual last name, as you might imagine, some text of some kind. Maybe even hyphens or apostrophe, but certainly not much more than that. But naturally, attackers don't do what is expected. They'll send in whatever they can get away with. So if they can get away with sending in a script into the last name field, they may do so in hopes that the web application will take this last name, or whatever that is, and incorporate it into the page that's going to be given back to the user. And graphically, we can kind of see that same attack here on the slide. So here, the user would click on this malicious link that's been kind of shortened so it'll fit. So we'll just pretend that the script is this evil function here. And that goes off to the web server. And the web server has a little snippet of code in it that says, well, whatever the value of the message is, whatever the value of the message parameter is, we'll just substitute that right here. And we'll say, hello, Mr. Anderson, or hello, script equals script. So that gets incorporated into the web page and then goes all the way back to the browser where it executes. Now, the web application, of course, is not harmed by any of this because web applications don't execute JavaScripts or queries or things like that. They just pass this information on, and then eventually it works its way back to the browser where the script would execute. So the issue here is that the browser, when everything's included in the page, the browser has a really hard time telling the difference between what the developer intended to be data, like text and numbers and things like that, from scripts that are syntactically correct. From the browser's point of view, if it's a script and it looks good, it'll go ahead and execute it, unless it's been marked as non-executable. So really, the root cause of these kinds of things is that the dynamic output is ambiguous from the browser's point of view. It really is not sure if the developer meant to include a script in the page or if somebody malicious somehow snuck that script in there and got it all the way back to the browser. So that leads us to this path relative style sheet injection. And in this case, we're not injecting the script tags that we looked at a minute ago. What we're actually injecting is style sheets, which is a type of script as well as JavaScript is. And usually it's used to format the page. So you'll send in styles that might turn the font bold or make the font bigger, perhaps insert images or put a background into the page. Essentially, the job of the styles is to alter what you would normally see from just the HTML and improve it or enhance the imagery in the page. So to kind of understand how the injection works, it helps to step back for a second and kind of look at how web pages are constructed, how browsers figure out what the paths are to these different resources that make up web pages, and how the web server does the same. So to start with, web pages are not actually made up of a page or a document. They're made up of lots of different documents that come from HTML, styles that we already mentioned, usually in the form of a CSS, JavaScript files, .js files, and some other files as well. Now, also, these elements can be intermixed with the HTML, but in our case, we're looking at the Matilde website, And we can see here on the left just a partial list of the various files that make up the web page that you see on the right-hand side. This list probably goes on double again, so you're looking at maybe like a third of the files that make up this page. Now, the very top get, if you will, that was fetched is the HTML that makes up the page itself. And then that HTML includes lots of links out to all of these other files that you see, a lot of those being pictures. You can see the .png extension and the GIFs and things like that. But there's also JavaScripts and style sheets that are fetched as well. So you can see the question mark picture shows up on the screen, and it's referenced about the 7th one down. The PHP logo shows up about 15 spots down, and all of those little elements were fetched separate from the actual, what we think of as the web page. So file references in HTML is what allows you to keep these elements of the page separate from the actual page itself. That way you don't have to run everything in line. I mean, you don't have to include all the scripts and all the styles and all the references to the images all just in one big giant document. You can split things up. So we can pretty much reference just about any element in the page. Technically, you can even reference other pieces of HTML and stuff in certain cases, and it's pretty common in the Ajax technologies. So in this picture here, we see the question mark and the PHP logo that we looked at earlier. And if you looked inside of the main page and you looked at the HTML, like in Firefox, you can hit Control-U or View Source, Internet Explorer, Safari, or similar, where you just view the source of the page. What you would actually see is you would see these references here that reference those images and pull them into the page at runtime. And of course, the browser was showing those actual live fetches that it was doing in real time. And it's pretty common to have these files, like these style sheets and these JavaScripts, off into separate files, because you might want to use that style sheet on 15, 20, 100 different web pages in your site. And so rather than cutting and pasting the contents of what would be in that style sheet into every single one of your web pages, it's good practice to put all that common code off into a separate page. And then the pages that need to use that functionality, just pull that in at runtime using these references that we looked at here a second ago. And of course, you would do that with images and VB scripts and any other common code that you might have that you want to share between pages. And that definitely is a great practice. So the tags that will do this would be tags like the link tag, anchor tags, which is just the letter A. And these kinds of tags, they have attributes that allow you to reference these external documents. So you'll see here in the link tag here, we're referencing a style sheet. We're pulling in a style sheet into our page. And we're using a relative link. So we're saying, starting from the current directory, go into the styles directory, and then grab style sheet global styles.css. We can see a JavaScript file included with the script tag using a similar methodology where you use the source attribute of the script tag to say, I want to pull in the JavaScript from the Matilda JavaScript folder, and its name is bookmarksite.js. Now, these links can be relative, like the ones we just looked at, or they can be absolute. An absolute link is one that's specified fully from start to finish. So, in an absolute link, you would need to reference HTTP, the server name, the full path, and then the name of the file. That's not best practice, and most sites won't do that, because the name of the site can change, the domain name can change, and if it did and you used absolute links, you'd have to go through your code and find all the places in the code where you had done that and then change it. So that's typically not done. Also, if your site ever went from HTTP to HTTPS and you hard-coded in HTTP, you're trapping the browser into HTTP mode. So again, best practice is you use these relative links. Now, the relative links always are referenced from the current page, which of course is relative. Depends on which page you're looking at. But whatever page that you're browsing to, these relative links start from that page's location and then move into the file system on the web server from that point forward. So how do browsers know the file path to these linked files? What's the mechanism they use to figure this out? And how they do this is not necessarily important as long as it works, but what we'll notice later is that how the browsers do it and how the web servers do it is different, and that is important. So first we'll take a look at the browsers. So we start with the base URL that we talked about a second ago. That's the page that you're looking at right now. The base URL is the URL for that page. That's the first page that was loaded into the browser that has these references to all these other files that are getting brought in to the page at runtime. After you do that, we append that relative path, that short snippet of path that refers to the file, to the end of the main path, and that gives us our absolute path. It gives us the full path to the file that we want to reference at runtime. And then the browser turns around and goes about the business of getting that file, pulling it in, and incorporating it into the page. This is all done automatically. You can kind of tell it's happening sometimes intuitively, because sometimes you'll notice that pages will load pretty well at first, and then there's maybe a big picture, or there's a large JavaScript file that kind of has to load, and maybe your page kind of gets stuck from your point of view, sort of halfway through, and you're waiting for it to finish rendering the rest of the content. And it could very well be because some kind of network congestion, or because you're trying to pull in a larger include file, that you're having to wait for that resource to come across. So if we look here, the current path of the main page that we saw a minute ago, if you recall, that was /Matildaday. It was in the Matildaday folder. That's where that main file was. And we have a reference, an href here, to stylesglobal.css. So the browser needs to put all that together, and that'll tell you the path on the web server of where you can find global.css. So browsers are working on these rules based on this RFC. And the browser is trying to figure out where the path starts based on the format of the URL. So here we'll see that based on these rules here, the domain name ends here after the first slash. Now that's a slash by itself. There's the scheme, HTTP, and then :/ that separates the scheme from the domain name. So that's not what the browser is looking for. The browser is actually moving past the domain name and looking for that first slash, and that's called root. And that is the first spot that we're going to start this path from. So in our case, our main page was in the Matildaday folder, and then its name is index.php. So the browser is going to match the file name located after the last /. So to get the base URL, how the browser does this is you figure out the file name of the web page. That was index.php. Take the file name off, and you're left with the path. That's the base URL. So in our case, the base URL is the blue part. It's the http matildaday.local domain name / Matildaday folder. And now we have our base path to start working from. So if we want to go fetch the global styles, we need to take that relative path that was referenced in the link, or if you prefer the JavaScript example we had earlier that was referenced by the script tag, we need to take that snippet, that relative URL, and put it onto the end of the base URL, and that gives us the full absolute URL to fetch this file. Now, how web servers do this is slightly different, and we need to watch carefully at how Apache figures this out. So if you look in the Apache configuration file on the web server, what you'll see is you'll see a regular expression that's going to match the file extensions that Apache is going to process. So you take PHP, for example, a common framework. PHP, like other frameworks, is not processed directly by the web server itself. So the web server is going to look out for pages that are Java, Cold Fusion, ASP, ASP.NET, PHP. And it wants to send those pages off to a processor, like a PHP processor, to go get the page for it so it can return the results back to the user, the browser. The regular expression here will match among a lot of other extensions PHP. You can see it starts with PH and then ends in P. Optionally, it can be PHP 3, PHP 4, PHP 5, so on and so forth. So there's lots of different extensions that'll match, but for our purposes, it matches .php just fine. So you'll notice that our index.php page is found just fine. Apache has no problem locating that page whatsoever, since the extension matches the regular expression that's looking for it. So far we know how the browser is getting the base URL and the absolute URLs for these resources, and we also know how Apache is figuring out what page to go get from the web server. And it turns out that in our example, even though they are using two different methods, it works out okay. So remember that the web browser figured it out because it was the file after the last slash, which was index.php. And the web server figured it out because it's matching on the file extension, index.php. So in both cases, the web server and the web browser have no problem, no disagreement whatsoever. They also agree that the path, the base path, is /Matilde. Everybody's on the same page. So where it gets a little bit tricky is that what if the URL is not in the expected format? So I think most of us, when we go to any web page, whether it be a common web page like Google or a bank or whatever your favorites are, you kind of expect the URL to start with HTTP or HTTPS, and then there's a domain name, and then you have some kind of a path, and then finally you get to the file name at the end. And if you've had to type any kind of URLs at all, then you're probably pretty used to this convention. But what happens when you get a situation like this, where the page is actually kind of in the middle of the path, and then you have some extra URLs, some extra slashes with some extra folder names at the end of the URL? And that is actually where it gets to be kind of interesting. So in the case of going back to how the browser calculates the paths, we said that you need to cross out the last file name, right? The thing after the last slash. So in our example here, the word bar is after the last slash. Browser needs to subtract that off. And then what's in blue is the base path that remains. So in order to figure out where that style sheet is, we cross out the last file name, that's the base path. We add the relative link from the link tag, put it all together, and then we get this URL here at the end. Now we know, from looking at the example earlier, that's not correct. But we'll have to see what happens as a result of that. Now if we look at that URL we generated, we're going to send that off to the web server, right? And the web server is going to try to go fetch that page. So browser is going to ask Apache for this file right here, because it calculated the path using the mechanism we talked about earlier. But the question is what's the web server going to do with that? Because that certainly doesn't match any real file. The path is clearly much longer than where the actual file is. Well, the web server is going to calculate the path using the other method. It wants to match on things that end in .php, right? So Apache applies the regular expression matching for .php along with those other extensions that it would allow. And honestly, the stuff after index.php really doesn't matter. From the web server's point of view, those are arguments maybe that the application needs to do some processing, like maybe some RESTful arguments or some other information needed by the application to process the page. From Apache's point of view, it says, yes, that's a .php file. Let me get that for you. And that's where the trouble begins. Because the browser asks for a style sheet, globalstyles.css. The web server saw that the browser wanted index.php, and clearly something's got to give. So Apache actually does return index.php, the real index.php, to the server. Because if you remember, back when you looked at the path, Apache didn't have any problem with this. And that is the real path to the index.php in our example. So index.php file will come back to the browser, but the browser is looking for globalstyles.css. So what happens when index.php shows up at the browser? Well, if we look in the web inspector here, we can see globalstyles.css is clearly what the browser thinks returned back from the web server. It even says it right here, globalstyles.css. But look carefully at the document type of the file that actually showed up at the browser. That's not a CSS. That is actually an HTML page. It is, in fact, index.php is what that page is, instead of globalstyles.css. So what's happened is that we've successfully been able to control, in this example, the page that has come back to the server, to the web browser, and it's a different page than a style sheet. So far, this really isn't causing much of a problem. We can see the page loaded okay. The page is probably not going to look right, but so far we haven't run into an issue. So the browser asks for the style sheet, and it gets back the index.php. And browsers don't really like that. If they expect to get back a style and the MOM type of the document doesn't match, they normally won't render that page. So index.php would not be used to build the web page that the user sees. It would just kind of be ignored or disregarded because its type is wrong. It had a doc type of HTML, and the browser knows it should be a doc type of CSS, media type of CSS. And usually that works, usually. So there's also another feature of browsers called the browser compatibility mode. And this is put into the browsers to make life easier on the developers. I'm sure it also helps protect market share for the browser manufacturers because a developer can kind of not quite get the page just right. Maybe the syntax is off a little bit. Maybe they're using some tags that are old and depreciated, no longer valid anymore. But the browser tries to be a little bit forgiving and let some of that stuff come through. It tries to do its best to parse these things. Usually the consequence is the page may not look quite right. It may not render as quickly as it should if the page was written correctly. But overall, if the developer is happy with it, they'll probably just let it be and let the compatibility mode take care of those minor issues. Now, sites can voluntarily enter into this mode in the browser. They can encourage the browser to use compatibility mode using a few methods. One is they can use this old doc type here, HTML 4.01 transitional. And this is a very old document type meant to help developers move from, like it suggests, HTML4 to later versions of HTML4 and eventually HTML5 in the long run. And it wasn't meant to be a permanent situation, but that's one way to kind of coax the browser into that mode. Also, you can just leave your doc type off your page entirely. I've seen a lot of pages that do that just because the developer doesn't know they should use a doc type. That's kind of unsafe not to use a doc type, and it just kind of gets forgotten, and the browser is fine with it anyway. The browser will just drop into compatibility mode and roll with it. So, also, as you may know, you can, and especially in Internet Explorer, makes it relatively easy to drop into compatibility mode because you may have seen that little broken page icon next to your URL bar that you can click to kind of help older pages render correctly in the newer versions of IE. And so you can put your browser into compatibility mode yourself. That's another way you might get into this mode. So back to the browser asking for a style sheet, but an HTML file showed up at the door. And we said before that the browser just kind of ignored that. The MOM types didn't match, it wasn't what was expected, and the browser just sort of moved on with its day. But in compatibility mode, that's not necessarily what happens. In compatibility mode, what the browser will do is it will scan through the HTML document that showed up, and it'll try to see if there might be some style in there. There might be some style tags or a style sheet that's embedded in that HTML page. And in compatibility mode, the browser will go ahead and try to use those styles, even though it showed up in the wrong kind of page. So now we've not only figured out a way to kind of affect what page is loaded in the browser, but with compatibility mode, our styles that are in this incorrect page may actually have a chance of getting executed now. We still have no way of controlling the style, though, right? It would just be whatever style happened to be in index.php by random chance. So now we move on to trying to figure out a way to inject some style into this page. So in order to do this, you're going to need to find a page that has a cross-site scripting vulnerability. any type will do. You could use stored cross-site scripting or reflected. The type is not so important. What's important is that you need a way of sneaking some style sheets or styles into the affected page at runtime, like the example we saw earlier, where we were using the last name field to kind of sneak that script into the page at runtime while the user was actually using the page. And if we can find a page like that, then this quirk and the difference between browsers handling the page and servers handling the page actually becomes useful. So one of the interesting things about styles is that they're actually a little bit simpler to inject sometimes than traditional cross-site scripts based on the JavaScript language. You see the example here. These two injections actually do the exact same thing. Both of them will try to find elements and parts of the page, in other words, and they'll try to turn the background behind those elements red. So this one here is the style version of it, and it uses what's called a selector, that little star there. That's a wildcard, and it basically means all elements. So that will try to turn the background of the entire page red, all elements. Then we have the script tag, which does something similar and tries to change the style using this attribute style connected to the elements. So it's looking for basically the first element, and it's going to turn the background red on that one. So what you'll see is that the JavaScript tag requires script tags to tell the browser what you see between these two tags is script that I need you to execute. It's called breaking out of the HTML context. But the style doesn't have any tags on it. And that actually makes it an easier injection in a lot of cases, because as these scripts have come along, there's been some naive defenses put into some products that just try to filter bad things out. And of course, if you've been in web security any time at all, you know that typically doesn't work out too well. But nonetheless, it's tempting for people to try to keep the so-called bad out, and they'll target things like script tags, thinking, well, how else would you be able to get a script in if you don't have the script tags? I'll just filter the tags out. And of course, the styles don't have any tags at all. And in fact, if you look at that character set, it's %0A, a couple of squiggly brackets, the stars, and alpha, and then a colon. Really, none of those characters seem to be particularly threatening if you look at the traditional list of characters that get filtered out by a lot of these filters. So we can take a look at how this works better using a bit of demonstration. And to start with, I want to break apart this injection here. Okay, so here is the path extension. Remember, we needed that to kind of set up the difference between how the browser is going to figure out the relative paths and how the server is going to do it. So we need to inject those in to get the to get that to work. And then we also need to, as Gareth Hayes, I think, if I remember his quote correctly, he said, we need this %0A to get the browser in the right mood, or something like that. It was pretty funny how he put it. And incidentally, he's the original discoverer of this vulnerability, as far as I know. His blog, anyway, was the very first one I ever saw mention this. And he ended up going to work for Portswigger, who makes the tool Burp Suite that you all might be familiar with if you're in web development. And so he actually works for that company now. And probably not coincidentally, Burp Suite is actually one of the very few scanners on the market that can detect this vulnerability. So maybe he worked on that project. But then we have this selector. This is the wildcard character in the blue. Now you could specify a particular element that you wanted to apply this style to. So you could put div or span or whatever your favorite tag is into there and specify to target particular spots on the page. But we're just using the wildcard to get started because it's easy to get warmed up if you just say, I don't care what the tags are. And then we'll have the actual payload. In this case, it's color::red, which is a style that, as you might imagine, turns color red. Specifically, in this case, what it does is it turns the font red. So the color attribute applies to font. And then we need to close out the injection with this suffix here, these two path separators, to end the injection. And the reason that's colored green is because you can kind of think of the foobar at the beginning and the double slash at the end. You kind of think of those as the suffix, the prefix and the suffix to kind of put your injection between. And so you can think of this stuff in the middle, this red part here, is kind of dealer's choice. It's up to you as to what you want to put in there. So if we look at a full URL, we'll see that we're going to actually put this injection here after the PHP page. Remember, we wanted to put it after the PHP part because the web server is going to be okay with figuring out that the PHP page needs to come back, and the web browser is actually going to go looking down here for the page. All right. And actually, in this presentation, I've got a list of styles that I've already tested that work that you could try, and so we'll be happy to forward these to you. And we'll start off maybe with like the color equals red one. All right, so let's go over to Safari. Okay, I guess a quick note on kind of the lab setup. So what I've done is I've run a vulnerable website that has this vulnerability implemented inside of it on purpose over here on just an Ubuntu virtual machine. And I've also have a Kali virtual machine running that we'll look at here in just a minute. And then finally I've got Safari, and Safari is just browsing to the Ubuntu virtual machine that has this website on here. So this website, Matilda2, has purposely put the path relative vulnerability into a page and has already set the browser into compatibility mode as best as a website can do to try to help you do this exploit for yourself in as easy as a way as possible. And the way that works is that we have a frame here that's framing this styling with Matilda area here in the center. And so that gives you a chance to kind of see how your injection is falling in the page. And it also outputs the path of the page that's framing it. So you might imagine this border is about right here, and then it's telling you styling.php is the page that's framing it. And that gives us a kind of a reference to work from. All right, so let's go down here. Let's see. Oops, went too far. So there's styling.php. And we said we needed to put a slash, and then we were going to put that path there. And then we needed, let's see, the percent and 0A. That is the line feed character. It's like a line break if you think about hitting like the enter key, for example. And then we needed the star, the selector, which was going to select all the elements. And then we were going to have the payload inside the squiggly braces. And then we were going to end it all in the double slash. And then we were supposed to be able to put our payload in between. And I'll check this real quick before we actually pull the trigger here. All right, so the one that we're trying to use is something like this one here. So, oh, and I think I forgot these squigglies that Gareth said got the browser in the view there. So let's see. So we'll put those in there. Okay, so the part we're injecting starts about right here and moves down to roughly about right there. Okay, now the stuff that's occurring after this in the URL, these are other different parameters that are being passed in the page legitimately. They're supposed to be passed in. So we'll hit enter, and then we can actually take a look and see why this is working. This is Safari, but Firefox has very similar tools in it. So if you're more used to Firefox, you can do basically this exact same thing, more or less. So over here in under the frames folder, under index.php, which is the outer page, we have the global styles.css being referenced. But look what showed up. It's actually index.php for the reasons we talked about earlier. And then if we scroll down just a little bit and look right here, we can see the injection occurring right over here, the foobar, and then the color red. So the browser must be in compatibility mode because the even though this index.php page is clearly HTML, there is some valid style in it, right? There's the color red is a valid style, and it's syntactically correct. And one of the things you'll notice about this page that's already been set up for you in the Matilde tool is that there's a meta tag that's trying to coax the browser into using the compatibility mode when displaying the page. And also it uses the HTML 401 transitional doc type as well. Again, just to try to help the user along. All right, so we can kind of see that that's working now pretty well. So turning the page red and doing some of these other styles is interesting because in effect we're starting to be able to control the content of the page to some extent. But even with some of these more advanced styles, we're still not really kind of hitting that home run where we're really sort of replacing the content on the page, really kind of controlling the content. So we might be able to work our way up to that though. If you look at some of these other styles, there's some other tricks in here that may come in handy. Styles can actually turn parts of the page invisible. So if you think about using a display none type of a filter in a page, what you may be able to do is selectively turn off parts of the page. And now you're able to start to control the content a little bit more. You can also combine the styles together. So we see here in this one, we have a color green and the font weight is bold. Oops, didn't mean to bold it. Sorry. All right, and we'll go back over here. Let's find the injection spot. And the point of this one is to show that you can start to string the styles together. You don't actually need to inject one single style and use that. So if I go ahead and put the font weight bold in there and the color green at the same time, what we end up doing is we get two styles applied where we have the bold text that's now the color green. Naturally, you can imagine stringing along many styles, flipping certain tags on and certain tags making it invisible, changing others, and starting to try to control the content of the page. You can also use some of the more complicated injections, and such as this one. And what this will do is it will kind of rotate the text around and turn things different angles. But the main reason I wanted to point it out is that when you get into a little bit more advanced injections, some of the characters that are actually in the style that you're injecting into the page may be characters that are also valid in, say, HTML. You could end up defacing the page the wrong way because your injection is not considered a style, it's considered HTML. Also, some of the characters you use in your styles may be characters that are used by Apache to process the web page itself. You could end up breaking Apache accidentally. The way to solve this problem is that what you want to do is you want to URL encode your injections. So like here you can see %3a, %20. %20 might be familiar to you, that's the space character. And you wouldn't want to have a space in your injection because it's a space, right? And then Apache may see that space and not recognize the rest of your injection. So by URL encoding these as you send them into the browser, you can input just about any injection you want. It'll safely get past the web server and make it all the way back to the web page and you get in the browser. Obviously, you can combine the encoding technique with being able to string the injections together. And so you end up getting the full package where you can have mainly arbitrarily long style injections to start to do lots of stuff to the page. But at this point, we're still not really replacing the content. Obviously, we're gaining a lot of control over the content, but not completely subverting it altogether. So one of the things you might consider doing is using something like this. We have our vulnerable web server that we've been picking on here for 5 minutes or so. And we know about our payload. But one of the things you might be able to do in your payload is try to pull content from a different web server that you control. So think about you having your own web server on the internet somewhere, and you put some content onto that server. You inject into the vulnerable server somewhere else, and have the vulnerable web page pull your content over at runtime when the user is looking at it. That can't be filtered out server-side because it's not happening server side, right? Your content's getting pulled over by the browser itself when it goes and fetches all the resources that are listed in the page to go fetch that we saw at the very beginning. So I'll copy this one. So let me try a different tab here. Okay, so to kind of break this down, I've got the vulnerable site that we've already been messing with, and the page to frame variable styling.php, the foobar setup, the %0a, and all that kind of good stuff. And then I'm referencing this server here, 172.16.0.199. Now, as it turns out, that is a web server that I set up here, 172.16.0.199, that I've got Apache, my own copy of Apache running on with my own content being served from that site. So now I can pull my own content over into the page coming from my server that is pushing the content of the legitimate web page down and out of the way and showing itself above the fold. And to take this a step further, instead of just pushing the content out of the way, you could go ahead and use some of those display none styles applied to specific tags to just go ahead and turn off the content of the particular page so it's invisible and only your content shows on the page. So in the finally, you might ask, well, how do you defend yourself against something like this? Because in the end, how do you control all these little quirks, this compatibility mode, all the these different vulnerabilities? It turns out that actually all you need to do is encode your output that you're getting from untrusted sources. So if you're selecting information from a database, or you're getting it from the user, like in this case where we're getting it from the URL that the user clicked on, when you encode that output, what you're telling the browser is that regardless of whether the data forms syntactically correct script, whether it makes sense as JavaScript or makes sense as a style, you're transforming it into such a way that the browser understands it's just data, and it'll just show the attack on the screen, but it won't actually execute it. And so output encoding is included in some frameworks, and you can also download help from OWASP and other places that have the ES API that's free, that'll have encoders inside of it that can do these types of encodings for you. So on the remainder of the presentation, I've actually got the steps to reproduce this, and we'll put those notes out on the ISSA website so that you can recreate the scenario. The Matilda 2 application is completely free, and it's pretty easy to install. It actually implements several dozen vulnerabilities. To get to this particular one, from when you come into the tool from the menu, if you go to, let's see here, cross-site scripting, and then go down to via path relative style sheet injection, it'll take you to the actual page, and you can give this a try for yourself. So we have a few minutes left. Is there any questions? Oh, sorry, yes.
So it sounded like the only protections available are on the developer side, not on the browser side. Is that correct?
Yes, that's correct. The browser, from its point of view, would have a hard time telling what scripts the developer wanted to intentionally include and what scripts are coming in maliciously. Because the script is actually going to the server first. The injection is going to the server first. It's getting rolled into the web page and then sent back. So the same origin policy is not violated. And legitimately, from the browser's point of view, it really is coming from the web server. So they're really, from the browser's point of view, I think the browser is pretty innocent in this case. Now, there are protections built into the browsers to varying degrees that'll try to look for so-called bad stuff, but we know that ultimately you can't block everything or else the user won't be able to use the site anymore. What else, please?
Can you show the examples of good practice?
I'm sorry?
Can you show the examples of good practice, how the developer...
How a developer would be better off?
Yeah.
Sure. In Matilda, if you toggle the security, it'll actually run a it'll run different code. And the way it works is that in level 5, right here where it says security level 5, where it's doing server-side security, it'll actually implement some of these controls that we're talking about. So you can go, it's completely open source, it's just PHP scripts. So if you come over to the code, in this case we had it on Ubuntu. So if we did gedit, and then, let's see, I think I have it in var www.html. So what you'll see when you go inside the source code is you'll see that it has different controls that it runs for like case 1 and case 5. And do you see down here in case 5, security level 5, see how it says encode output is true? And so when we go down to where it actually does the, where it actually takes in the input, if that's true, then what it does is it calls the OWASP ES API encoder, and it encodes whatever information is being sent into the page through these variables. And that way, when it outputs it to the user later, you're going to tell the browser, hey browser, no matter what you see here, even if it's good script, just display it on the page. It's just data. And so that ES API encoder there actually encodes it first. And then down here, when you actually echo the page title out, for example, as one of the variables, it'll be encoded in that security level 5. Does that make sense?
Yep.
Yeah. There's a lot of, I guess, learning features built into Matilda 2 like that, where it runs both the vulnerable code and the fixed code. And certainly, if you want, try security level 5 and see if there's any way you can figure out to break it. If there is, I'll fix it and tweet your name out as someone who found one of the security level 5 bugs. All right. If you need help, if I toggle back into the regular mode and then hit toggle hints, click on hints, and then click on the hint that you want help with. So in our case, we were talking about path relative style sheet injection. It'll open up a new tab for you that'll walk you through how to do these, just a little bit at a time. All right. Well, thanks very much for everybody coming today. Appreciate it.